The Domain of Cancer Statistics, a presentation by Professor Gershom Zajcek, Faculty of Medicine, Hebrew University of Jerusalem. While in acute conditions medicine made tremendous progress, in chronic conditions it fails. The main reason for this are corrupt statistics which guide treatment. Medical statistics applies methods which are adequate for machines and not for humans. The founders of medical statistics adopted machine statistics since in the world of machines they are successful and even vital. They were not aware of the fact that as such these methods are not suitable for medicine and have to be adapted and modified. And I discuss it in several presentations like the central fallacy of medical statistics, survival analysis, and medical models. So here are some definitions for cancer statistics. Incidence, the number of newly diagnosed cases during specific time period. Mortality, the number of deaths during a specific time period. Prevalence, new and pre-existing cases for people alive on a certain date. And survival, the proportion of patients alive at some point subsequent to the diagnosis of their cancer. I shall discuss breast cancer statistics, and here are my definition. Case is a woman with a tumor, and the incidence, the number of newly diagnosed cases of women with tumor during a specified time periods. Mortality is the number of dead cases, patient with a tumor, during a specific time period. So cancer statistics deals only with cases with a tumor. No tumor, no statistics. Breast cancer progression. Cancer starts when a normal stem cell becomes malignant, which is called transformation. Initially, here you have the transformation. Initially, the tumor is too small to be detected. You have small tumor and cluster, and it grows, and when reaching the detection threshold, it is diagnosed. This event is also called tumor surfacing. So the detection threshold determines when we are aware of the tumor or when it is diagnosed, and it is called generally incidence, and the death is called mortality. Now, we are talking about clinical cancer, but we know that cancer starts much earlier. So we have cancer and we have a clinical cancer. What does it mean? Diagnosis is incidence of a single case. Since in preclinical period women do not have a detectable tumor, they are not regarded as cases. Clinical cancer is the domain of cancer statistics. So cancer statistics doesn't have anything to say here. So this, because they don't know, they don't have a detectable tumor. Cancer statistic is only during its clinical phase of cancer. So here you have the preclinical, no tumor found, clinical, tumor found. The domain of cancer statistics extends from diagnosis to death. Cancer statistics do not apply to preclinical cancer, and therefore we have two sorts of survival. Real cancer survival from here to here, and clinical cancer survival, which we call also observed survival, OS. Again, preclinical, no tumor, no visible tumor, clinical tumor. So there are two sorts of survival: real cancer survival and clinical cancer survival, which we call also observed survival, or OS. And there is a rule: OS is always smaller than real survival, and OS is not proportional to real survival. They do not have a constant ratio. So once you know the behavior of OS, you cannot extrapolate in order to define, know what the real survival is. So incidence and clinical survival depend on the resolution power of medical imaging. Cancer statistics domain also depend on incidence. So here, for instance, you have manual. These women detected the tumor in the breast through manual examination. And they had this kind of survival. But once you go to mammography with X-ray, you detect the tumor when it's a little smaller and earlier, and therefore you have a longer clinical survival. And the same is with computed tomography and other imaging. If you detect the tumor earlier, you get also a prolonged survival, and not only this, you get a broader domain of cancer statistics. So cancer statistics relevance depend on the incidence. Example. We are talking about two sorts of mammography: X-ray mammography and CT mammography. Obviously, CT mammography sees a little smaller tumors, and we can say that CT survival is longer than X-ray mammography, simply because CT detects the tumors earlier or when they are smaller, and this is called varying incidence. So here you have two curves, this time compared with manual survival. These women detected the tumor in their breast manually, and this went to mammography with X-ray, and obviously they have a better survival, because also you see the domain is longer. So both OSX and OSM are subset or projection of the real cancer survival. Although you have a difference between these survival curves, it is not a real difference, because both groups have one real survival, which we don't know. We try to estimate. Cancer recurrence incidence. Usually we call it cancer recurrence, but it's also incidence, and it is problematic in the same way like I discussed before. So here we start with stem cell transformation. We have the diagnosis incidence, and then immediately the woman is treated, surgery, but in many cases surgery leaves behind some tumor remnants which they don't see during treatment, and they start to grow, and then we have recurrence, and it's an incidence recurrence, like the incidence of diagnosis, because it depends on the detection threshold, like this one. So here's another aspect of this, that usually we read in publication cumulative recurrence, like this one. Again, we start with diagnosis, like here, and we have a cumulative, and these women in whom treatment left behind some tumor. But it is called cumulative recurrence, but it ought to be called cumulative recurrent incidence, because it has also the similar difficulties like before, it has a varying incidence. Now, it is interesting to know that cumulative recurrence and progression-free survival are related statistics, because you can get it 1 minus progression-free survival, you get cumulative recurrence. So it's the same kind of survival depending on incidence, progression-free survival. So let's go another example. We are talking about recurrence again with the same story. How do we determine that the incidence of a recurrence? Are we using X-ray devices or CT devices? So each one detects the tumor at a different threshold, and you get again survival of recurrence of CTs better than survival of X-ray, the same phenomenon like before, and here you have it summarized, that as you go and look for the recurrence earlier, you get better imaging devices, you get prolonged survival. So here you have again X-ray detected recurrence, and you see this curve, cumulative, and you ask yourself, is it the detection threshold X-ray or detection threshold CT or MRI? All these incidences determine how this curve will, the outcome of this curve. So it's a real unreliable curve. So most studies do not report which imaging devices were used, or so you don't know how reliable this curve is. The same applies to surrogate endpoints, which are also unreliable. So let's look what is a surrogate endpoint according to the FDA. Surrogate endpoints are used when the clinical endpoints might take a very long time to study. Clinical trials are needed to show that surrogate endpoints can be relied upon to predict or correlate with clinical benefit. So what do they suggest? So you have here surrogate endpoints, potential substitute for clinical endpoints, and you check blood pressure and LDL, HbA. So let's see how these surrogate endpoints determine the survival of patients. Again, you have the same story. Each biomarker has a different tumor incidence. I describe it here. And again, viral, you get this one. LDL, this one. The same story, because it is incidence of surrogate endpoints. So there is a fallacy of cancer statistics, this incidence. Domain of clinical cancer spans between two events, incidence and mortality. Cancer statistics regards them as scalars. In reality, incidence is not a scalar. It is a binary couplet, a function of detection threshold. So you see, incidence is a function of an event when it occurs and the detection threshold. And statistics, generally, what you see in all publications, they take incidence and mortality as equivalent, which is a fallacy, as you see. Statistics derived from incidence are flawed. These are cancer incidence, cancer recurrence, and surrogate endpoints. So let's get rid of incidence. Is it possible to define cancer statistics without relying on this incidence? Yes. Let's regard cancer as a process. So here is a summary what are survival functions, and we are interested mainly in the hazard function, and you can read how you derive it. We are talking about hazard rate or hazard function. Example, this survival distribution describes survival of cars. Hazard rate is the probability of a car to die, so-called, in the next moment. And here hazard rate is constant. But note, there is no incidence here. They have a paradise. Survival of machines without, because the incidence is when the machine leaves the factory. So, hazard rate. We abandon incidence. Here you have the tumor, the two clinical phases, preclinical, clinical, and we are talking about a process which extends from here to here. And all what we need to know is the hazard rate of this process. Even here, we suspect that the patient has something, we determine the hazard rate. And then we know how she advances during cancer. There is a unique epidemiological attribute of cancer which you don't find in the literature. The survival function or survival of all cancer is concave up. The survival of non-cancer, health and chronic diseases like diabetes is concave down. It's very interesting phenomenon. And this is also related to the hazard rate. Cancer of adult, hazard rate always declines. Observed hazard rate. And here you have lung and pancreas. In normal population, hazard rate rises, and also in diabetes, etc. This is called force of mortality. It's very difficult to grasp what this means, and I suggest you read some of my presentation to get used to this. Hazard rate declines. But it's real. It's there. So let's do a thought experiment. We take two groups of women, healthy women and women with breast cancer. Each group there are 1,000 women here and 1,000 women here, and obviously we don't know which one is healthy and which one is not healthy. And what we do is, at midnight, we count the number of women who died since last midnight and compute the hazard rate of each group. And you will see that healthy women, hazard rate will rises, and women will continue to decline. So we can diagnose, or we can know which one has cancer without examining the women. I repeat, we have two groups of women. We don't know which group is healthy, which group has cancer. Without examining the women, by the shape of the hazard rate, we can say these are non-cancer and these are cancers. Again, it's very difficult to grasp. Go to other presentations. So what does it mean? I don't care what this group has. All I need to know the hazard rate of this group with time, and I know when it goes up, hazard is, I have to do something with my treatment. When it goes down, I can relax. Again, I described in another presentation. So let's look at such a hazard rate in the SEER statistics. Here you have survival of 300,000 patients, which extends for 30 years, observed survival or clinical survival, indicating that breast cancer is a chronic disease. Here is the hazard rate computed from this population, and again I describe it in the presentation. Bimodal hazard rate and tumor growth in breast cancer, which also specify where in the sphere I took the data. And what you see here, that the hazard rate is fluctuating. Initially it goes up, it goes down, and at any point I show this hazard rate, you can estimate the growth rate of the tumor and how the woman feels. Note that the survival curve is smooth. You don't see this fluctuation in this survival curve. Why? Observe the ordinate. On the left, the ordinate goes from 0 to 1, and here from 0 to 0.006. So these observed survival, which cancer statistics so love, don't show you the real thing, because they don't fluctuate. Hazard rate is 100 times more sensitive and therefore reveals important features. Conclusion. You wonder, how may hazard rate be estimated while women enjoy life? Because we estimate it from their death. You can estimate it. Some clues I mentioned in other presentation, and I shall discuss it also in depth in other presentation. So next, you are invited to listen to dynamic cancer survival function, which deals with the same phenomenon which I just mentioned. Enjoy.